Welcome curious minds and sleepy thinkers. Settle in and let the gentle rhythm of these words guide you toward a soft place to land. As the world outside grows quiet, we will journey inward, not to the familiar shores of everyday thought, but to a silent, contemplative space where the questions are vast and the pace is slow enough not to jolt you out of your pillow cocoon. There is no need to rush, no need to understand everything at once. We are here simply to wonder. Tonight, we will drift through one of the most mysterious and beautiful ideas in all of science, the cosmic speed limit. It is a speed so fast that it seems to defy our imagination, yet it is a boundary so constant, so unyielding, that it defines the very structure of our reality. It is the speed of light. To begin this quiet exploration, let's step away from the world of numbers and equations, and instead imagine the universe as a grand and ancient library. Not a library filled with books, but with laws. These are not man-made laws, but fundamental truths, elegant and simple rules that govern every particle, every star, every galaxy. One of the most foundational laws etched into the very fabric of this cosmic library is about speed. It decrees that there is an absolute maximum speed at which any information, any particle, any force can possibly travel. This speed, this universal ceiling, is a constant and unblinking, unwavering number. It's approximately 300,000 kilometers every second, a value so immense that it is almost impossible for our minds to truly grasp its meaning. It is the speed of a single photon, the particle of light, as it streaks through the empty vacuum of space. But the true wonder of this speed is not just its staggering magnitude. The real mystery lies in the fact that it is a limit. It is a universal law that states nothing absolutely. Nothing with mass can ever reach this speed. The speed of light is not just a fast speed. It is the ultimate speed, the final destination on a cosmic highway with a fence that no one can climb. Let's try to understand this profound barrier, not through harsh mathematical proofs, but through a gentle metaphor, one that we can hold in our minds. Imagine, if you will, a small empty boat floating on a vast and perfectly still lake. If you were to give this boat a gentle push, it would glide smoothly across the surface. The water offers almost no resistance. Now let's add a layer to this gentle image. Let's imagine that as you push this boat faster and faster, the water around it doesn't stay the same. Instead, it becomes thicker and thicker, turning from a clear liquid into a heavy molasses-like substance. The faster the boat goes, the denser the liquid becomes, creating a powerful resistance that grows with every ounce of effort you put in. To get the boat to move even a tiny bit faster would require a monumental push, an effort far greater than the one before. It's as if the lake itself is pushing back, resisting the boat's motion with an ever-increasing force. This simple image holds a quiet truth about our universe. In the world of Isaac Newton, a world we still live in and understand every day, if you apply a constant force to an object, it will continue to accelerate its speed, increasing indefinitely. There are no speed limits. But in the world of Albert Einstein, a world that reveals its deeper truth at extreme velocities, this intuition, this old friend of a concept, gently parts ways with us. Einstein's theory of relativity tells us that as an object with mass accelerates and its speed approaches the speed of light, something fundamental happens to it. The energy we pour into it to make it go faster doesn't just increase its speed. It begins to manifest as an increase in its relativistic mass, or its inertia, its resistance to further motion. It is a quiet paradox. The energy is not lost. It is simply transformed. It's like a river that flows into a great thirsty sponge. You pour in more and more water, but instead of the river flowing faster, the sponge simply gets bigger and heavier. The energy you're providing doesn't just make the object move, it makes the object itself heavier, more resistant. This isn't a physical increase in the number of atoms, but a profound increase in its inertia. An object at 99%, the speed of light is so much more massive in this relativistic sense than it was at rest that it becomes incredibly difficult to accelerate it further. The energy needed to give it just one more tiny push is far greater than all the energy before it. Now imagine what would happen if you tried to push it all the way to the speed of light. As the speed gets closer and closer, that relativistic mass would begin to grow infinitely large. And to accelerate an object with infinite mass would require an infinite amount of force, an infinite amount of energy. It is a logical wall, not a physical one. And since an infinite amount of energy is not a thing we can create or find, it is simply and beautifully impossible for any object that has a non-zero rest mass to ever reach or exceed the speed of light. It is an intrinsic unbreakable law of physics, a design feature of reality itself. It's the universe's way of ensuring that certain things remain constant and in balance. And what are the beautiful, gentle consequences of this profound speed limit? For one, it gives our universe a sense of narrative of story. It is the reason we can, in a sense, look back in time. When we gaze up at the night sky, we are not seeing the universe as it exists right now in this very moment. We are seeing it as it was when the light we are receiving first began its long, lonely journey toward us. The light from our sun, for example, takes just over 8 minutes to reach us. So the sunset you admire is a memory, a picture of the sun as it was 8 minutes in the past. Light from our nearest stellar neighbor, a small red star named Proxima Centauri, takes just over 4 years to reach us. When we see it, we are seeing light that left it during a time when much of our world was in a very different place. The light from the great Andromeda galaxy, a beautiful spiral of 1 trillion stars, takes a staggering 2.5 million years to arrive. Every time we catch a glimpse of that hazy smudge in the sky, we are looking into a distant ancient past. We are seeing the ghost of a galaxy from a time when our own distant ancestors were still walking the earth. Without the cosmic speed limit, without the finite travel time of light, the universe would have no history to reveal to us in this way. All the light from all the stars would arrive at our eyes at the same instant, and the cosmos would be a flat, timeless canvas. It is this beautiful, gentle delay, this cosmic postal service, that gives our universe its depth and its story. This idea of light traveling, of it having a finite journey, is not something that humanity always understood. In fact, for thousands of years, the simple everyday experience of light led us to the exact opposite conclusion. Let's imagine ourselves for a moment in a world before electricity, before modern clocks, before our current scientific understanding. We are sitting in a dark room. Someone lights a candle, and in that same instant, the entire room is filled with light. The shadows are banished. The shapes of the furniture are revealed, and the space is transformed. There is no perceptible pause, no moment of waiting. To the human eye and the human mind, the change is instantaneous. From this simple, profound experience, it was entirely logical to conclude that light had no speed at all, no journey to make. It was not a traveler, but a state of being. It simply was. The universe had built-in rules, and light was not subject to the same laws of motion that governed everything else. This question whether light appeared everywhere at once, or if it had to travel, was one of the most fundamental mysteries ever pondered by the human mind. It was a question tied to the very definition of our perception, to the very nature of reality itself. A philosopher sitting under the vast and quiet night sky would look up and wonder, when I see that distant star, am I truly seeing it as it is now? Or is there a gentle, unseen pause between its being and my seeing? This simple, beautiful curiosity, born from the contemplation of a flickering flame, would lay the groundwork for centuries of scientific inquiry. It would become a puzzle that would challenge the greatest minds of different eras and different cultures. It was not a question that could be answered with a flash of inspiration alone, but would require careful observation, meticulous experiments, and a quiet, stubborn refusal to accept the obvious. The journey to understand the speed of light is in many ways the story of humanity's journey from philosophical deduction to scientific experimentation. It is a story of how we learned to listen to the whispers of the universe and how we learned that even the most seemingly simple phenomena are often hiding the deepest and most profound truths. And in this quiet understanding, we find not a limit, but a beautiful invitation to simply wonder. Let's drift now from the quiet contemplation of the modern mind and journey back in time over 2,500 years to the sun-drenched shores and bustling forums of ancient Greece. This was a time when the lines between philosophy poetry and what we now call science were beautifully blurred. Here the first seeds of the great question we just explored: does light travel? And if so, how were planted not by men with high-tech instruments, but by thinkers with only their eyes, their curiosity, and the simple phenomena of the world around them. Their tools were not lenses or clocks, but logic and imagination. And the answers they cultivated were a world away from our modern understanding, rooted not in measurement, but in poetic intuition and the very nature of human perception. Our journey through this garden of ancient ideas begins with Empedocles, a Greek philosopher from the island of Sicily, who lived around 490 to 430 BCE. His theory of vision was one of the earliest and most beautifully intuitive attempts to explain how we see. For him, the act of seeing was not a passive reception of something from the outside world. Instead, he believed that a special internal fire emanated from the eye itself. He called this fire the allovium. Imagine for a moment the human eye not as a window receiving light from the outside world, but as a tiny living sun, a small flame that sends out its own rays to meet the world. When this fire streamed forth from the eye, it would interact with the objects around us, and in that moment of contact, we would see them. This was a radical idea for his time, one that put the power of sight not in the object, but in the observer. The eye was not a passive cup to be filled, but an active creative force, a kind of beacon in the night. Empedocles' theory, while ultimately incorrect, contained a profound whisper of a truth that would lie dormant for centuries. He also suggested that light itself was composed of tiny, rapidly moving particles. This was a truly revolutionary concept for a time. By describing light as a traveling entity made of particles, he implicitly suggested that it must have a finite speed, even if he had no way to measure or even prove such a speed existed. It was the first inkling of light as a physical phenomenon with a journey, rather than just an instantaneous presence. His vision of sight was less a scientific model and more of a poetic act of touch, the eye's light reaching out to feel the world, to make an intimate, energetic contact with it. His ideas, so deeply tied to the natural elements of fire and earth, were a testament to a mind that sought to understand the universe through elegant metaphorical systems, and in doing so, he planted the very first seed of the idea that light might be a traveler. Following in his wake, another giant of Greek thought, Plato, the master of philosophical dialogues, built upon these emissions theories in his famous dialogue, Timaeus. For Plato, vision was not a simple act, but a convergence of three separate fires. There was the fire from our eye, the internal light streaming forth much like Empedocles' idea. There was the external light from the sun, and finally, the light reflected from objects in the world. He envisioned these three fires coming together at a single point, a moment of union, where the act of seeing occurred. It was a beautiful and intricate dance of light, a handshake between the sun, the eye, and the object. Like his predecessor, Plato's theory also involved light moving or streaming from the eye, implying a process over time rather than an instantaneous event. But for Plato, the exact nature of this movement and its speed was not the central focus. His concerns were far more ethereal. He was more interested in the philosophical implications, the link between perception, reality, and the forms that lay behind the physical world. For him, the questions were about truth and illusion, about the fleeting nature of our world and the eternal perfect forms that gave it shape, not about the gritty mechanics of kilometers per second. Now let's turn our attention to a very different kind of mind, one who focused less on the metaphysical and more on the tangible, on the beauty of logical order. Euclid, known to us as a brilliant mathematician, Euclid, who lived around 300 BCE, approached light not as a substance or a philosophical principle, but as a geometric puzzle. In his work, Optics, he established a principle that, to this day, forms the foundation of our understanding of light. He established that light travels in straight lines. This was a beautiful and significant observation, so simple it almost seems obvious, but its implications were profound. Imagine light not as a mysterious fluid, but as an invisible, perfectly straight arrow, an unwavering line stretching from a source to an object. This simple rule allowed him to explain phenomena that we take for granted today: how shadows are cast, how we see reflections in a mirror, and the basic workings of lenses. He could, with a simple diagram, explain why a shadow is a perfect ghost of the object that casts it, why a reflection in a still pool is a mirror image of the world above. While Euclid did not explicitly claim that light had a finite speed, his concept of light traveling along a specific defined path subtly reinforced the idea that it was a physical phenomenon that occupied time. It wasn't a state of being that appeared everywhere at once. It was a journey, and a journey requires a path, a specific trajectory through space. His geometric approach to light, though simple, laid an essential foundation for all later studies in optics, providing a language for describing how light behaved in space, even if the question of its fundamental nature remained unanswered. The elegance of his work was so compelling that it became a foundational block upon which future thinkers would build. But the most influential voice in the ancient world, the one whose shadow would fall across Western thought for over 1,000 years, was Aristotle. His view on light was a dramatic departure from the ideas of Empedocles and Plato, and it was so compellingly intuitive that it held sway for an immense stretch of history. He argued that light was not a movement of particles or waves, not a stream of anything, but rather an actuality or a quality of a transparent medium. For Aristotle, to have light was to have a medium like the air or the water in an illuminated state. There was no journey. There was just a change of state. Think of it like this: if you have a perfectly transparent pane of glass and you illuminate it with a flashlight, the glass itself becomes illuminated. The light isn't a thing that travels through the glass. The glass simply becomes lightened. It's like a piece of music not traveling to fill a concert hall, but the hall itself in an instant becoming a place of sound. The medium in this case, the air, is the key. When a source of light like a candle is present, the transparent medium becomes illuminated. There is no motion to measure, no journey to embark upon. The change is immediate. This perspective led to a very clear and intuitive conclusion: light's appearance was instantaneous. There was no journey to be made, no speed to be measured, because light was a state, not a motion. The moment a candle was lit, the air became illuminated, and the effect was immediate throughout the entire space. This idea, so simple and so consistent with everyday experience, was backed by the immense authority of Aristotle, a figure whose intellectual gravity was so great that his pronouncements were almost beyond question. His work was a massive, comforting anchor that held the ships of scientific inquiry in place for centuries. For over a millennium, the idea of light being instantaneous was the dominant thought, the unquestioned truth. Challenging this idea was not just a matter of a new theory. It was a profound intellectual undertaking, an act of rebellion against the established order of the world. Now let's pause and consider for a moment the world these thinkers inhabited and the limitations they faced. Their theories were a beautiful blend of keen observation and imaginative deduction. They saw the world around them the way a room fills with light, the way a shadow falls, the way a reflection shimmers, but they had no tools to measure the fleeting passage of time in increments smaller than a heartbeat. They were trying to understand a phenomenon that on our human scale is always and forever instantaneous. The speed of light is so immense that any journey we could witness with our own eyes appears to be without duration. From the moment we strike a match to the moment a distant wall is illuminated, our senses register no delay. And so the conclusion of Aristotle, the most logical and rational mind of his era, was a direct consequence of this human limitation. Empedocles saw the power of the eye and imagined it as a source of fire, a creative force in the act of seeing. It was a poetic and empowering idea. Plato saw the sun and the eye as partners in a cosmic dance with the object of sight as their meeting point. It was a metaphysical and beautiful conception of reality. And Euclid, with his passion for order, saw the straight lines in nature and gave light a geometric elegance. Finally, Aristotle, the great synthesizer and organizer of all knowledge, looked at a room being filled with light and gave it a simple, powerful explanation that perfectly matched the observation. Each of these ideas was a masterpiece of its own kind, a reflection of a mind trying to make sense of a world without a proper scientific language for it. They were building the first maps of a new territory, and the maps were of course filled with unexplored spaces and mythical creatures. They were flawed, not because of a lack of intelligence, but because of a lack of tools. But without these initial poetic attempts, without these first guesses, the path to a more precise understanding could never have been forged. They set the stage for the centuries to come for the thinkers who would finally dare to challenge Aristotle's immense shadow and to ask a question that would ultimately lead to a revolution in physics. And perhaps that is the most beautiful thing about these ancient ideas. Their flaws are not a sign of failure, but a testament to the raw, untamed power of human curiosity. They show us that the journey of understanding always begins with the courage to simply wonder, and that sometimes the most profound intellectual act is to challenge the most obvious truth. As the sun set on the great civilizations of classical Greece and Rome, a quiet twilight descended upon Europe. The vibrant forums of philosophical debate grew silent. The grand libraries of Alexandria and Athens were lost to time, and the careful logical inquiries of the ancients were largely left behind like forgotten relics. But the flame of knowledge, that most precious and fragile of human possessions, did not die out. It was carried on a gentle wind and found fertile ground in another part of the world, in the blossoming intellectual centers of the Islamic Golden Age. In this era, while Europe was in the midst of its long and introspective slumber, brilliant minds across the Middle East and North Africa were busy building a bridge, a beautiful and vital span of thought that would connect the poetic intuitions of the Greeks with the rigorous empirical science of the European Renaissance. This was a time of immense intellectual curiosity, a period that lasted for several centuries and saw the rise of a new kind of scholar. These thinkers were not content with merely preserving the ancient texts. They were meticulous translators, but also restless innovators. In bustling cities like Baghdad, a new kind of hub emerged, the House of Wisdom, a great library and research center where the texts of Plato, Aristotle, and Euclid were not just read, but were lovingly translated, debated, and most importantly, challenged. This was a place where mathematics, medicine, and astronomy flourished, and where the first seeds of the scientific method, the belief in observation and experiment, were carefully sown. It was a time of quiet yet profound revolution, and at the heart of this revolution in optics was a figure who would change our understanding of light forever. His name was Ibn al-Haytham, known in the West by his Latinized name Alhazen. Born in Basra in what is now Iraq in the year 965, he was a true giant of his time, a polymath who had a profound grasp of mathematics, astronomy, and physics. But his most revolutionary and lasting contributions were in the field of optics, the very subject we are exploring. He was a man who possessed a calm yet fiercely rigorous mind, and he dared to challenge the most deeply held belief of the ancient world, the emission theory of vision that had been passed down from Empedocles and Plato for over 1,000 years. This was a theory that saw the human eye as an active transmitter, a small sun sending out its own invisible fire to touch the world and bring it into our consciousness. Alhazen looked at this ancient idea and found it wanting. He asked simple, elegant questions that were like tiny pebbles dropped into a placid pond of thought, creating ripples that would grow into waves. If our eyes truly send out a fire, he reasoned, why is it that we can't see in the dark? The fire from our eyes should still be there, and yet we see nothing. Why is it that our eyes are hurt when we look directly at the sun, a far more powerful source of light? If our eyes' fire was meant to touch the world, why would a more powerful fire cause us pain? These simple, beautiful questions, so obvious in retrospect, pointed to a profound and different truth. Through careful observation and relentless reasoning, Alhazen concluded that vision occurs not because something leaves our eyes, but because something enters them. He proposed that light from an external source like the sun or a flame reflects off the objects in the world and then travels in a straight line to our eyes where it is received. It was a profound and revolutionary paradigm shift, a quiet but monumental inversion of a centuries-old idea. He cast the eye not as a beacon shining into the world, but in its true role as a passive receiver, a delicate window to reality, a complex and beautiful instrument designed to gather the light of the cosmos. This insight was the first great step on the path to a modern scientific understanding of light. Of Alhazen's masterpiece, his great and enduring work was a monumental treatise called Kitab al-Manazir, or the Book of Optics, written between 1011 and 1021. In it, he laid out his theories with a level of scientific rigor that was centuries ahead of its time. He was not content with mere philosophical deduction, a reliance on elegant but unproven arguments. He was an empiricist, a man who believed that the truth was to be found not in the polished words of a scholar, but in careful, controlled observation, and most importantly, in the verdict of experiment. His work was a radical departure from the tradition of the Greeks, a silent declaration that the world would reveal its secrets, not to contemplation alone, but to careful investigation. He conducted groundbreaking experiments with the camera obscura, which we know today as the pinhole camera. Imagine a small, completely dark room with just a tiny hole in one of its walls. Outside, in the bright sunlight, stands a beautiful lit candle. Alhazen observed that a perfect inverted image of that candle would appear on the opposite wall of the dark room. He understood that this was not a magic trick, but a simple, elegant proof that light traveled in straight, defined paths. The light from the top of the candle passed through the tiny hole and landed at the bottom of the image, and the light from the bottom of the candle passed through the same hole and landed at the top. The image was a direct inverted projection of the reality outside, a beautiful testimony to the simple rule that light follows. He also demonstrated that this phenomenon held true no matter what shape the light source was showing, that each point on the source sent light in a straight line through the hole. While he acknowledged that light must travel, he too struggled with the immense speed of it. He lacked the tools to actually pin a number on its speed. He knew intuitively that if light were truly instantaneous, it would be difficult to explain certain observed phenomena, such as how our perception of a distant flash of light seemed to require a moment of time. But he had no way to measure that moment. The speed was simply too great for the technology of his era. His genius, therefore, lay not in providing a final answer, but in providing a new and correct framework for the question. He moved the study of light from the realm of pure philosophy, where ideas were judged by their elegance and intellectual harmony, to the realm of experimental science, where ideas were judged by their alignment with observable reality. His quiet but firm emphasis on controlled observation and experimentation was a critical transformative step forward for the entire human endeavor of science. Alhazen's work, a profound whisper in its time, would become a loud roar centuries later. It was translated from Arabic into Latin in the 12th century, and its influence spread slowly but surely throughout Europe, carried by the hands of curious scholars. His ideas directly inspired the great thinkers of the Renaissance and the scientific revolution. When later European scholars, men like Kepler and Galileo, began their own investigations into light and vision. They stood not on the ancient shaky ground of Aristotle's instantaneous light, but on the new solid empirical foundation that Alhazen had laid. He was a bridge, a vital and luminous link in the chain of human discovery, ensuring that the flame of inquiry would not be extinguished, but would in time be reignited with a new and more powerful kind of fire. He didn't just preserve knowledge, he transformed it gently, guiding the world toward a more rigorous and truthful way of knowing. He showed that the surest path to understanding the cosmos is not to simply wonder at its mysteries, but to ask it gentle questions and listen carefully to the answers it gives. As the intellectual bridge built by Alhazen was finally crossed, Europe began to awaken from its long philosophical slumber. The flame of curiosity, which had been so carefully tended in the East, was carried westward and began to burn with a new and brilliant intensity. This era, known as the European Renaissance and the subsequent scientific revolution of the 16th and 17th centuries, was a time of immense intellectual vigor. The prevailing view, still largely anchored by the immense authority of Aristotle, was that light was instantaneous. But a new spirit of inquiry, fueled by a growing emphasis on observation and a bold willingness to challenge old dogmas, began to stir the waters. The time for mere philosophical speculation was coming to an end. It was time to start asking the universe to show its hand. Among the early voices in this reawakening was René Descartes, a brilliant French philosopher and mathematician who lived from 1596 to 1650. Descartes, whose ideas would shape the intellectual landscape for centuries, also contributed to the ongoing discussion about the nature of light. While he championed a mechanical view of the universe, his theory of light aligned with the prevailing instantaneous view. He imagined light not as a stream of particles or a wave, but as a pressure or a tendency to move, transmitted through a perfectly rigid and continuous medium that filled all of space, which he called the plenum. To understand this, let's imagine a perfectly straight, infinitely long, and perfectly rigid rod. If you were to push one end of this rod, the push would be transmitted to the other end instantaneously. There would be no delay, no journey in time. For Descartes, light was like this push, an immediate propagation of a state, a pressure that was felt everywhere at once. While his concept of a physical medium foreshadowed later ideas about the ether, his conclusion of light's instantaneous nature reinforced the Aristotelian view and kept the question of a finite speed at bay for many of his followers. But it was against this backdrop of philosophical speculation and a prevailing belief in instantaneous light that the first truly scientific attempt to measure its speed was made. This monumental effort, a quiet but profound act of intellectual courage, was undertaken by Galileo Galilei, the renowned Italian polymath often credited with ushering in the era of modern experimental science. Galileo was a man not content with the comforting unproven pronouncements of the past. He was a man of action, a man of curiosity, and he believed that if light had a finite speed, no matter how fast it was, it should in principle be measurable. His approach was pragmatic, ingenious for its time, and a hallmark of the new scientific spirit. Galileo's experiment, likely conceived around 1638 and described in his posthumously published book, Discourses and Mathematical Demonstrations Relating to Two New Sciences, was simple in its elegance and almost poetic in its setup. He proposed that two observers, each equipped with a lantern that could be quickly covered and uncovered, position themselves at a significant distance from one another. Let's imagine Galileo himself and an assistant. The first observer, Galileo, would uncover his lantern. As soon as the second observer, the assistant, saw the flash of light from Galileo's lantern, he would immediately uncover his own. Galileo, in turn, would measure the time it took from when he first uncovered his lantern until he saw the light from the assistant's lantern return. This total time measured would represent the sum of three distinct intervals: the time it took for the light to travel from Galileo to the assistant, the time it took for the assistant to react and uncover his lantern, and finally, the time it took for the light to travel back from the assistant to Galileo. It was a clever, simple, and beautiful idea. By conducting the experiment over different distances, Galileo hoped to isolate the time taken for light's journey. For instance, if they performed the experiment over a distance of 1 mile, and then again over 10 miles, the difference in the total measured times after accounting for the constant of human reaction time would in theory reveal the time light took to cover the additional distance. Galileo and his assistant attempted this experiment. They tried it first over short distances on land, and then reportedly over greater distances, perhaps even between 2 hills, separated by several miles. It must have been a beautiful and humbling sight. 2 lonely figures standing miles apart in the dark, sending their flickering fire signals back and forth across the night, each trying to catch the elusive fleeting passage of light. They found, however, that for any practical distance they could manage, the time interval they measured was indistinguishable from the interval they observed when they were standing very close to each other. The humbling truth was that the time it took for light to travel the distance was far, far too short to be distinguished from the time it took for the human observers to react. A human reaction time, which is typically a few tenths of a second, completely dwarfed the actual travel time of light over such distances. To put it in a more concrete way, for a light signal to travel 1 mile and back, it would take roughly 11 millionths of a second, a period of time. So tiny it is utterly meaningless to a human mind with a lantern. The entire time measured was for all intents and purposes simply the sum of 2 human reaction times. Galileo, with his characteristic honesty, concluded that if light did have a finite speed, it must be extraordinarily fast. Far too rapid to be measured with the technology and methods available to him and his team. He famously stated, "I have tried the experiment, and the result was that it was impossible to discern whether the light of the first lantern was seen at the instant of its exposure, or whether it traveled from the one place to the other with a perceptible interval of time." He did not succeed in measuring the speed of light, and in that his experiment was a failure. But in a far more important way, it was a profound and lasting success. First and most crucially, it represented a monumental shift in scientific methodology. Instead of relying on the comfortable cloak of philosophical deduction or the dogma of religious texts, Galileo adopted an empirical, hands-on approach. He asked a question and then, with a clear mind, devised an experiment to test it. This was the hallmark of the burgeoning scientific revolution, the belief that the universe's truths were not to be found in old books, but in careful observation and measurement. Second, his experiment, despite its negative result, did not prove that light was instantaneous. Instead, it strongly suggested that if light had a speed, it was so incredibly high that human perception and simple mechanical means could not detect the delay. This kept the question of a finite speed alive and ensured that it would not be dismissed as a mere curiosity. It moved the problem from the realm of philosophical speculation, where it had rested for thousands of years, to the realm of experimental physics, where future generations of scientists would be spurred to devise more sophisticated and precise methods. The challenge of measuring such an immense speed was daunting, even for the most brilliant of minds. The speeds we encounter in our daily lives, a galloping horse, a swift arrow, a cannonball fired from a great distance, are all so slow compared to the speed of light that the concept of a finite speed for light seems almost counterintuitive. It's a bit like trying to measure the shadow of a thought. It feels immediate, but in reality, there's always a tiny, almost imperceptible delay. Galileo's genius was not in finding the answer, but in even conceiving of the question in such a way in providing a path forward for others to follow. His effort was a true pioneering moment, a courageous attempt to test the limits of what was knowable. The simple, elegant failure of his experiment was therefore not a failure of the hypothesis, but a powerful testament to the universe's own grandeur and speed. It planted a quiet but profound seed in the soil of science, a seed that would one day blossom into the definitive discovery that light was indeed a traveler with a finite and measurable speed, a speed that would ultimately define the very fabric of spacetime itself. His work marked a decisive step away from the ancient philosophical debates and a step toward a new era of scientific rigor. He had shown that some of the universe's most profound truths were not to be debated, but to be discovered, and that the path to discovery lay in the patient and painstaking work of observation and experiment. The stage was now set for a new kind of drama, a drama of measurement where the cosmic speed limit would finally reveal itself, not on a mountaintop, but across the vast and empty distances of the solar system. The flickering lanterns of Galileo and his assistant, though they failed to measure the fleeting speed of light, had done something far more important. They had planted a seed of doubt. For centuries, the question had been debated in philosophical terms, a matter of elegant rhetoric and intuitive deduction. But Galileo, with his simple pragmatic experiment, had moved it firmly into the realm of the measurable, and in doing so, he showed that the answer, if it was to be found at all, would not come from a book, but from the universe itself. The challenge was immense, a towering mountain of a problem. If the distances on Earth were too small, and the human reaction time too great, then a new kind of laboratory would be needed, a laboratory of unimaginable scale, one that could only be found in the quiet, star-filled void of space. And so we leave the mountaintops of Italy and drift through the silent expanse of the cosmos, guided by the slow, stately dance of the planets. It was in this grand celestial clockwork that the first definitive and truly astonishing answer would finally be revealed. The man who would read the universe's secret was a Danish astronomer named Ole Rømer, working in the prestigious Paris Observatory in 1676. He was a meticulous and patient man, a kind of cosmic detective whose work was a quiet act of observation, a gentle gaze fixed on the celestial dance of Jupiter and its moons. Specifically, Rømer was focused on Io, the innermost of Jupiter's 4 largest moons. Io is a fast-moving moon, completing its orbit around Jupiter in just under 2 days. From Earth, we can watch it periodically disappear behind Jupiter and eclipse, and then reappear. These events, a kind of celestial game of peekaboo, were predictable. Based on Io's known orbital period, Rømer and his colleagues had compiled extensive tables forecasting the exact moment these eclipses should occur. But as they continued their observations over many months, Rømer began to notice a peculiar systematic pattern, a subtle but undeniable discrepancy in the timing. It was as if the cosmic clock was running a little bit fast and a little bit slow, but not at random. The pattern was tied to Earth's own stately journey around the Sun. When Earth was moving away from Jupiter in its orbit, the eclipses of Io consistently appeared to be delayed, happening later than predicted. It was as if the universe was holding its breath. Conversely, when Earth was moving towards Jupiter, the eclipses appeared to occur earlier than predicted. It was as if the universe was rushing to meet us. The maximum delay or advance that Rømer observed was about 11 minutes when Earth moved from its closest point to Jupiter to its furthest point. This was not a tiny, insignificant error. It was a profound puzzle. Rømer, with a flash of brilliant insight, correctly deduced that these variations were not a quirk of Io's orbit, as some skeptics suggested. No, the puzzle was not in Jupiter's neighborhood, but in the vast empty space between us. The discrepancies, he realized, could only be explained if light took a finite amount of time to travel the changing distance between Earth and Jupiter. When Earth was further away, the light from Io's reappearance had to travel an extra distance to reach us, causing a delay in our observation. When Earth was closer, the distance light had to travel decreased, causing the eclipses to appear earlier. The universe was simply a vast theater, and we, the audience, were in a seat that was constantly moving. In a presentation to the French Academy of Sciences in 1676, Rømer explained his findings. He calculated that it took light approximately 22 minutes to cross the diameter of Earth's orbit. This was the moment that centuries of philosophical debate finally gave way to a concrete, if slightly flawed, number. Based on his 22-minute estimate and the best available, though not perfectly accurate, estimates for the size of Earth's orbit at the time, Rømer calculated the speed of light to be roughly 210,000 kilometers per second. While his value was about 25% lower than the currently accepted speed, his method was sound, and his discovery provided the first definitive experimental proof that light travels at a finite speed, finally laying to rest the ancient philosophical question. It was a monumental achievement, and it proved that the universe was a place of delicate, beautiful delays, not one of instantaneous presence. Despite Roemer's compelling evidence, his discovery was not immediately and universally accepted. His mentor, the great Giovanni Domenico Cassini, remained skeptical, preferring to attribute the observed discrepancies to irregularities in Eo's orbit rather than the finite speed of light. But over time, as further astronomical observations confirmed the pattern Roemer had identified, his explanation gained wider acceptance. A new age of measurement had begun. Following Roemer's breakthrough, the next great frontier in measuring the speed of light shifted from the vastness of the cosmos to the controlled, intricate environment of the laboratory. The goal was to conduct measurements entirely on Earth, a terrestrial experiment that would provide a more precise and repeatable result than could ever be achieved by gazing at distant moons. This was a significant challenge because even over the longest distances achievable on Earth, light travels incredibly fast, making the time intervals extremely short and difficult to measure with the available technology. Precise clocks, delicate optical instruments, and most importantly, clever experimental setups were needed. The first successful terrestrial measurement was performed by the French physicist Hippolyte Fizeau in 1849. His experiment was a landmark achievement, the first time the speed of light was measured without any reliance on astronomical distances. Fizeau's setup was a triumph of mechanical ingenuity and intellectual clarity. He used a rapidly rotating toothed wheel, much like a gear with many teeth and gaps. A beam of light was shown through one of the gaps in the wheel. After passing through the gap, the light traveled a significant distance, about 8,633 meters or over 5 miles, to a distant mirror. The mirror reflected the light back along the same path toward the rotating wheel. Here was the crucial, elegant part of the experiment. The returning light had to pass back through the same gap in the rotating wheel to be observed by Fizeau. If the wheel was rotating at a certain speed by the time the light returned, the gap it had originally passed through might have moved on, and a tooth might now be in its place blocking the light. But if the wheel rotated at a specific faster speed, the next gap would precisely align with the returning light, allowing it to pass through to the observer. By slowly increasing the rotation speed of the wheel, Fizeau could observe when the returning light was first blocked by a tooth, then when it reappeared as the next gap aligned, and then when it was blocked again. By measuring the rotation speed of the wheel at which the light was blocked or reappeared, and knowing the number of teeth on the wheel, Fizeau could calculate the tiny fraction of time it took for the light to travel to the mirror and back. Knowing that total distance, he could then calculate the speed of light. Fizeau's toothed wheel had 720 teeth. He found that at a rotation speed of approximately 12.6 revolutions per second, the returning light was completely blocked by a tooth. At twice that speed, or about 25.2 revolutions per second, the light reappeared, meaning the next gap had moved into position. Using these measurements, he calculated the speed of light to be 315,000 kilometers per second. This was astonishingly close to the modern accepted value and significantly more accurate than Roemer's astronomical measurement. Fizeau's experiment was a beautiful triumph of terrestrial measurement, showing definitively that the speed of light could be determined with precision on Earth without relying on the unpredictable movements of celestial bodies. Just a few years later, another French physicist, Léon Foucault, developed an even more precise method. Foucault's experiment, performed in 1862, utilized a rapidly rotating mirror instead of a toothed wheel. This method was technically more challenging, but offered greater accuracy. In Foucault's setup, a beam of light from a source was directed at a rapidly spinning mirror. As the mirror spun, it reflected the light beam toward a stationary mirror located a considerable distance away. After reflecting off the stationary mirror, the light traveled back to the rotating mirror. During the minuscule time it took for the light to make this round trip, the rotating mirror would have spun through a small but measurable angle. Because the mirror had rotated, the returning light beam would be reflected at a slightly different angle compared to the initial outgoing beam. This slight deflection of the returning beam was then measured. By precisely measuring this angle of deflection and knowing the speed of the mirror's rotation and the distance to the stationary mirror, Foucault could calculate the time it took for the light to make the round trip. His experiment yielded a value of 298,000 kilometers per second, even closer to the modern accepted value than Fizeau's. Foucault's method had another profound impact beyond just providing a more accurate measurement. He also used his apparatus to compare the speed of light in air and in water. His experiments unequivocally demonstrated that light travels slower in water than it does in air. This finding was extremely significant because it directly contradicted Isaac Newton's particle theory of light, which had predicted that light particles should speed up in a denser medium. Conversely, Foucault's results strongly supported Christian Huygens' wave theory of light, which had predicted that light waves would slow down when entering a denser medium. Foucault's experiment thus provided crucial evidence that solidified the wave theory of light as the dominant paradigm of the 19th century. Towards the end of the 19th century and into the early 20th century, the American physicist Albert Abraham Michelson dedicated much of his career to achieving even greater precision. Michelson's work was meticulous and groundbreaking, and he became renowned for his highly accurate measurements. He initially refined Foucault's rotating mirror method, and his measurements from 1879 yielded a value of 299.910 kilometers per second, the most accurate to date. Michelson continued his efforts, and in the 1920s, he undertook his most ambitious measurements. He conducted experiments over very long distances, using large rotating mirrors between two mountain peaks in California, Mount Wilson and Mount San Antonio. The distance between these two peaks was approximately 35 kilometers. He used a powerful light source and a system of rapidly spinning octagonal mirrors. The light would travel from one peak to the other, reflect back, and strike the rotating mirror again. By precisely adjusting the rotation speed of the octagonal mirror until the returning light beam was perfectly reflected to the observer, Michelson could calculate the time of travel and thus the speed of light. His measurements from 1926 gave a value of 299.996 kilometers per second, a value breathtakingly close to what we know today. Michelson's relentless pursuit of precision culminated in a final, even more ambitious set of experiments in the 1930s, conducted in a long vacuum tube to eliminate the effects of air on the light path. These later measurements, along with others performed by different scientists around the world using various techniques, consistently converged on a single highly precise value. The pursuit of the speed of light, which began with Römer's cosmic observation, culminated in 1975, when the International Bureau of Weights and Measures formally adopted a value for the speed of light in a vacuum, 299,792,458 meters per second. This value was so precise that in 1983, the meter itself was redefined in terms of the speed of light. The meter is now defined as the distance light travels in 1/299,792,458th of a second. This means that the speed of light in a vacuum is no longer something that needs to be measured repeatedly. It is a defined constant. The journey to measure the speed of light was a testament to human ingenuity, a story that began with a philosophical question and ended with a universal constant. It was a journey that took us from the flickering lanterns of Galileo to the rotating mirrors of Michelson, from the distant dance of Jupiter's moons to the quiet hum of a vacuum tube in California. It showed that with enough patience and enough curiosity, even the most fleeting and elusive of the universe's truths could be pinned down, a beautiful and humbling reminder of the power of the human mind to unlock the secrets of the cosmos. Having measured the speed of light with ever-increasing precision, The brilliant minds of the 17th, 18th, and 19th centuries were left with a new and even more profound question. It was no longer enough to know how fast light was traveling. Now they had to ask, what is light? What is this strange, luminous traveler that moves so fast it almost defies measurement? Is it a stream of tiny, discrete particles, like grains of sand? Or does it behave like a wave, a gentle ripple spreading across a vast and unseen ocean? This question, seemingly straightforward, would lead to one of the longest-running and most beautiful controversies in the history of science. A quiet debate that spanned centuries and would ultimately reveal a deeper, more complex reality than either side could have ever imagined. Let's begin our journey into this controversy in the 17th century, a time that saw the rise of two titanic figures, each with a completely different vision of what light was. On one side stood the towering figure of Sir Isaac Newton, the English physicist and mathematician whose mind reshaped our understanding of the universe with his laws of motion and universal gravitation. Newton, whose brilliance seemed to touch every corner of the known world, proposed a theory that was both elegant and intuitive. He believed that light consisted of a stream of extremely small discrete particles, which he called corpuscles. To Newton, the universe was a grand, beautiful machine, and light was one of its gears. The corpuscular theory, as it came to be known, explained several observed phenomena with a simple, reassuring logic. Imagine for a moment light as a vast swarm of tiny, perfectly spherical billiard balls, so small as to be invisible. The phenomenon of reflection where light bounces off a smooth surface could be easily understood. When these tiny billiard balls struck a smooth surface, they would bounce off in a predictable manner, with the angle at which they hit the surface being equal to the angle at which they bounced off. It was a perfect clockwork explanation for a phenomenon that had always been a mystery. But Newton's theory also took on the greater puzzle of refraction, the bending of light, as it passes from one medium to another, for example, from the air into a calm, clear pool of water. To explain this, Newton proposed that as his light corpuscles entered a denser medium, they experienced a force that pulled them towards the normal and imaginary line perpendicular to the surface. This force would cause the particles to accelerate, much like a marble, rolling down a gentle ramp gathering speed as it descended. Therefore, according to Newton's corpuscular theory, light should travel faster in a denser medium, like water or glass, than it would in air. This specific prediction, this quiet whisper of a hypothesis, would later become a crucial test, a cosmic coin toss between two opposing views of reality. Another strong point in favor of the corpuscular theory was its ability to explain the formation of sharp, distinct shadows. If light traveled as distinct particles in straight lines, then when these particles were blocked by an opaque object, they would simply cast a clear, sharp shadow with a distinct boundary between the light and the dark. This was precisely what we see in our everyday lives, a crisp, clean edge to the shadows that fall from our hands on a sunny day. This concept of light traveling in perfectly straight lines, known as rectilinear propagation, was a natural and beautiful consequence of the particle view. Newton's immense scientific authority and the success of his other laws meant that his corpuscular theory of light gained widespread acceptance, particularly in his native England, and it would dominate scientific thought for more than 100 years, casting a long and powerful shadow of its own over the intellectual landscape. Now let's turn our attention to the other side of this great debate, to a brilliant Dutch physicist, astronomer, and mathematician named Christiaan Huygens. Huygens, a contemporary of Newton's, held a very different and for a long time less popular view. He advocated for a wave theory of light. For Huygens, light was not a stream of particles, but rather a series of waves or vibrations that propagated through an invisible elastic medium that filled all of space. He called this mysterious substance the luminiferous ether. To understand Huygens' vision, let's imagine dropping a single pebble into a perfectly still pond. The pebble doesn't travel to the edge of the pond. Instead, it creates a series of ripples, a beautiful circular wave that spreads outward from the point of impact. For Huygens, light was like this ripple, a disturbance in a medium, not a thing in itself. His wave theory was based on a simple but profound principle, now known as Huygens's principle, which states that every point on a wave front, the leading edge of a propagating wave, can be considered as a source of new spherical wavelets. These wavelets expand outward, and the new wavefront is formed by the envelope of all these secondary wavelets. It's a beautifully elegant way of describing how a wave moves through a space, a kind of self-perpetuating cosmic rhythm. This principle allowed Huygens to explain reflection and refraction from a wave perspective, just as Newton had. For reflection, he showed how if waves struck a smooth surface, the secondary wavelets would combine to form a reflected wavefront that obeyed the law of reflection. For refraction, however, his wave theory made a prediction that was in direct, beautiful contradiction to Newton's. Huygens argued that when a light wave entered a denser medium like water, the wave's speed would decrease. This change in speed would cause the wavefront to bend, leading to the phenomenon of refraction. This was the first major point of conflict between the two theories. Newton said light sped up in water. Huygens said it slowed down. One of them had to be wrong. This simple, elegant difference in prediction would lie at the heart of the debate for centuries, a quiet intellectual duel waiting for a decisive blow. Huygens's wave theory also offered a natural explanation for phenomena like diffraction, the gentle bending of light around obstacles, or its spreading out after passing through small openings. While Newton's particle theory struggled to explain why light didn't always cast perfectly sharp shadows and sometimes showed slight spreading, the wave theory could account for this bending behavior, just as water waves will spread out after passing through a gap in a breakwater. However, the evidence for diffraction was not as clear-cut in the 17th century, and the effects were often subtle, making the intuitive particle explanation of sharp shadows seem more convincing to many. A significant challenge for Huygens's wave theory was the concept of the luminiferous ether. If light was a wave, what was it waving, and sound waves need air to travel? Water waves need water. If light traveled through the vacuum of space to reach us from the sun and the stars, then the ether had to be everywhere, a vast, invisible, undetectable ocean filling the entire cosmos. Describing the properties of this hypothetical medium, a medium that had to be rigid enough to support waves at such high speeds, yet tenuous and frictionless enough to offer no resistance to planets and stars, as they moved through it, became a significant hurdle for the wave theory. It was a beautiful idea, but it was built upon a substance that seemed to possess contradictory and almost magical properties. For over a century, Newton's enormous reputation and the intuitive clarity of his particle theory meant that the wave theory of light remained a minority view. But the tide, like a slow-moving ocean current, began to turn dramatically in the early years of the 19th century, thanks largely to the work of a brilliant English polymath named Thomas Young. Young, a physician, physicist, and linguist, provided the kind of compelling experimental evidence that could no longer be ignored. Young's most famous experiment, often called the double-slit experiment, was a breathtakingly simple and elegant demonstration of light's wave-like nature. In 1801, Young devised an experiment where he allowed a beam of light to pass through two very narrow, closely spaced slits. If light were a stream of particles, he reasoned these particles would simply pass through the slits and create two bright lines on a screen behind them, a simple logical outcome. But what Young observed was entirely different, a kind of cosmic poetry. Instead of two bright lines, he saw a beautiful pattern of alternating bright and dark bands, or fringes. This interference pattern was the unmistakable hallmark of wave behavior. When two waves meet, they can either reinforce each other, creating a bigger wave, constructive interference, a bright fringe, or they can cancel each other out, creating a flat spot, destructive interference, a dark fringe. This is precisely what happens with water waves or sound waves, and Young's experiment demonstrated that it was also happening with light. This phenomenon was impossible to explain with particles traveling in straight lines, and it provided powerful evidence that light was indeed a wave. Young's work was quickly and powerfully supported by the French engineer and physicist Augustin-Jean Fresnel, who developed a comprehensive wave theory with mathematical precision. Fresnel's work was so rigorous that it made a bizarre and counterintuitive prediction that was put to the test. A critic of Fresnel's, a mathematician named Siméon Poisson, used Fresnel's equations to argue that if a perfectly opaque circular obstacle was illuminated by a point source of light, then, according to the wave theory, there should be a tiny bright spot precisely at the center of the shadow cast by the obstacle. This prediction seemed absurd, a kind of mathematical joke, but in 1818, another French physicist, François Arago, performed the experiment and, to everyone's astonishment, observed the bright spot. This striking experimental confirmation, which came to be known as the Poisson spot, provided powerful evidence in favor of Fresnel's wave theory. The final nail in the coffin for Newton's particle theory came from the decisive experiments of Fizeau, and more conclusively, Foucault, whose work we explored in our last chapter. While Fizeau and Foucault were primarily trying to measure the speed of light, Foucault's experiment in 1862 had a beautiful secondary result. He used his apparatus to compare the speed of light in air and in water. His experiment definitively showed that light travels slower in water than it does in air. This was a direct, irrefutable contradiction of Newton's prediction and a perfect confirmation of Huygens's wave theory. It was the decisive blow in a centuries-old debate. With Foucault's result, the scientific community largely accepted that light was a wave. The focus then shifted from asking if it was a wave to asking what the nature of the medium, the luminiferous ether, was. It was a victory for a new kind of thinking, a triumph for the quiet, subtle elegance of the wave model over the intuitive, straightforward simplicity of the particle model. But as we will see, this victory was not the end of the story. The paradoxes of the ether would set the stage for an even greater revolution. A quiet, brilliant mind in the 20th century, a man named Albert Einstein, who would look at the problem and realize that both sides of the debate, in a strange and beautiful way, had been right all along. But that is a story for another time. For now, let us simply rest in the gentle knowledge that even the greatest minds can be nudged by the universe into a new, more truthful way of seeing. The truth, it seems, is not always the most obvious answer. With the wave theory of light having triumphed over the particle theory, the scientific community now faced a new profound mystery. If light was indeed a wave, what was it waving in? The very nature of a wave in the classical physics of the time was a disturbance in a medium. Sound waves require air or water to travel. Water waves need water. Without a medium, how could a wave exist at all? The space between the stars was a vast and seemingly perfect vacuum, a great emptiness. Yet light traveled across these immense distances from the sun to the earth and from distant stars to our eyes. To solve this puzzle, the scientific community led by thinkers like Christian Huygens adopted and refined the concept of the luminiferous ether. The luminiferous ether, often simply called the ether, was a hypothetical medium proposed to fill all of space. Its primary purpose was to provide a physical substance for light waves to propagate through. For many scientists of the time, the idea of a wave traveling through an absolute vacuum seemed counterintuitive, even impossible. The ether was envisioned as the universal medium for light waves, a silent, ubiquitous ocean that permeated even the vacuum and provided the necessary substrate for light to travel across the vast emptiness of the cosmos. But to serve its purpose, this ether had to possess some truly paradoxical and almost magical properties. Let's imagine for a moment the kind of substance we would need to invent to fulfill this role. First, for light to travel at such an incredibly high speed, the ether had to be extremely rigid or stiff like a solid. A very rigid medium is what allows for the rapid transmission of vibrations and thus very high wave speeds. Second, this ether, this cosmic solid, also had to be incredibly tenuous, massless, and frictionless. Planets and stars moved freely through space for billions of years without any noticeable drag. If the ether were dense or viscous, it would slow them down, and that was clearly not observed. So we had to imagine a substance that was a rigid solid, yet completely massless and frictionless. Third, it had to be completely transparent and undetectable by any means other than the propagation of light itself. It filled everything, yet it was invisible and insensible to every other force. The properties required of the ether were therefore quite contradictory. It had to be a rigid solid to transmit transverse waves. Light waves were understood to be transverse, vibrating perpendicular to their direction of travel, but also completely frictionless and massless, to allow objects to move through it unimpeded. This paradox began to pose significant theoretical challenges as the 19th century progressed. One of the central assumptions of the ether theory, and a natural consequence of classical wave mechanics, was that the ether provided an absolute reference frame for light. This meant that the speed of light denoted as c would only be c when measured relative to the stationary ether. If an observer or a light source was moving through the ether, then the measured speed of light would appear different, either faster or slower, depending on the observer's motion relative to this stationary medium. This was analogous to sound waves. The speed of sound is constant relative to the air, but if you measure the speed of sound from a moving car, it will appear different depending on your motion relative to the air. This concept led to the idea that it should be possible to detect Earth's motion through the ether. Earth orbits the Sun at a speed of approximately 30 kilometers per second. If the ether was stationary, then as Earth moved through it, there should be an ether wind blowing past Earth. Similar to how a moving car experiences a wind even on a perfectly calm day, this ether wind should affect the measured speed of light depending on the direction of measurement. For example, light traveling in the direction of Earth's motion through the ether should appear to be traveling slower, while light traveling against the ether wind should appear to be traveling faster. This theoretical prediction spurred several experimental attempts to detect the ether wind, a kind of cosmic barometer for our motion through the invisible medium. The most famous and meticulously performed of these experiments was conducted by Albert Abraham Michelson, the same physicist we met in the last chapter, and Edward Morley, an American chemist and physicist, in 1887. Their collaboration in Cleveland, Ohio, aimed to directly detect the relative motion of Earth through the luminiferous ether. The Michelson-Morley experiment was designed with extraordinary precision, a testament to the ingenuity of the human mind. It utilized an interferometer, a delicate device Michelson had invented, which could detect extremely tiny differences in the speed of light over different paths. The core idea of the interferometer was a beautiful one. It was designed to split a single beam of light into two beams that traveled along different perpendicular paths and then recombine them. Imagine a beam of light hitting a half-silvered mirror, a kind of magic window that both reflects half of the light and allows the other half to pass straight through. One beam travels straight ahead to a mirror and back. The other beam travels to the side to a mirror and back. When the two beams return to the half-silvered mirror, they are recombined and sent to a telescope where they create an interference pattern, a beautiful pattern of alternating bright and dark fringes. The genius of the setup was its sensitivity to relative changes in the speed of light. The entire apparatus was mounted on a massive stone slab, which was then floated in a pool of liquid mercury. This allowed the entire apparatus to be rotated smoothly and precisely, so that the two light paths could be oriented in different directions relative to Earth's presumed motion through the ether. According to the ether theory, as the apparatus was rotated, the light traveling along the arm parallel to Earth's motion would be affected by the ether wind, experiencing a slight delay in its round trip, compared to the light traveling along the perpendicular arm. This difference in travel time, though extremely small, was calculated to be detectable by their sensitive instrument. The interference pattern, the beautiful fringes, should have shifted as the apparatus rotated, a gentle nod from the universe that the ether was real. Michelson and Morley carefully performed their experiment, rotating the apparatus and making observations over many hours and at different times of the year to account for Earth's changing direction of motion in its orbit. The whole scientific world waited with bated breath. The prediction was clear. The experiment was flawless in its design. The shift should have been there, but to their astonishment and to the astonishment of the entire scientific community, they found no detectable shift in the interference pattern. Regardless of the orientation of the apparatus or the time of year, the speed of light appeared to be the same in all directions. The expected effect was simply not there. The result of the Michelson-Morley experiment was a null result, a profound and beautiful puzzle. The significance of this null result was immense. It directly contradicted the prevailing ether theory, which had been the cornerstone of light propagation for decades. If the ether existed and was stationary, the effect should have been observed. The failure to detect an ether wind meant that either the ether did not exist, or it possessed properties so bizarre as to make it undetectable, or that light itself behaved in a fundamentally different way than previously imagined. It was one of the most significant negative results in the history of science, leading to a deep crisis in physics. Various attempts were made to explain away the null result while preserving the ether concept. One famous proposal came from George Fitzgerald and Hendrik Lorentz, who independently suggested that objects moving through the ether would physically contract in the direction of their motion, and that clocks would slow down in just such a way as to precisely cancel out the expected effect of the ether wind on light speed. This Lorentz-Fitzgerald contraction was a clever mathematical patch, an attempt to save the ether theory by introducing new unproven physical effects. While these mathematical transformations would later become fundamental to Albert Einstein's special theory of relativity, their original motivation was simply to preserve the existence of the ether. Another idea, called the ether drag hypothesis, suggested that the Earth somehow dragged the ether along with it, but this was contradicted by other astronomical observations. The Michelson-Morley experiment's beautiful failure to detect the ether wind gradually led many physicists to question the very existence of the luminiferous ether. The properties required for the ether were becoming increasingly contradictory and complex, stretching the limits of believability. It needed to be a perfect fluid for celestial motion, but a perfectly rigid solid for wave propagation. It had to be ubiquitous, yet utterly undetectable. The elegant simplicity of light traveling without a medium began to seem more plausible than the increasingly contrived properties of the ether. The true and definitive solution to the ether problem came with Albert Einstein's special theory of relativity in 1905. Einstein completely discarded the concept of the luminiferous ether altogether. Instead, he based his theory on two fundamental postulates, which we will explore more deeply in our next chapter. The second of these revolutionary postulates stated that the speed of light in a vacuum is the same for all inertial observers, regardless of the motion of the light source or the observer. Einstein's second postulate directly explained the null result of the Michelson-Morley experiment without needing any ether or any ad hoc contractions. If the speed of light is truly constant for everyone, no matter how fast they are moving, then there is no need for a special medium or a preferred reference frame. The ether, having no observable effect and leading to theoretical contradictions, became unnecessary, a beautiful but ultimately incorrect idea that could be set aside. The abandonment of the ether concept was a profound paradigm shift in physics. It meant that light, unlike other waves familiar at the time, did not require a medium to propagate. It was an electromagnetic phenomenon that could travel through the pure emptiness of space by virtue of its oscillating electric and magnetic fields. This was a radical departure from classical physics, which always sought a mechanical explanation or a medium for wave propagation. The demise of the ether had far-reaching consequences. It cleared the way for a deeper understanding of the fundamental nature of space and time themselves, and it set the stage for one of the greatest intellectual revolutions in human history. The Michelson-Morley experiment, therefore, did not merely fail to find something. Its quiet, beautiful null result forced humanity to fundamentally rethink its place in the cosmos and to embrace a universe that was far stranger and more elegant than we had ever dared to imagine. The grand intricate debate between the particle theory of light and the wave theory had finally reached a temporary conclusion. With Foucault's experiment proving that light traveled slower in water, the elegant, intuitive simplicity of Newton's corpuscles had been gracefully set aside, and the wave model championed by Huygens and mathematically solidified by Young and Fresnel had taken its place as the reigning truth. But this triumph did not bring a final peace. It simply led to the next great question, a question born of the very nature of waves. What was the medium for this wave? The ether, a strange, beautiful substance of contradictory properties, was the accepted answer. Yet as we saw with the Michelson-Morley experiment, this ether seemed to be invisible and undetectable, a ghost in the machine. A new kind of thinking was needed, a new lens through which to view the universe, and so we now turn to one of the most brilliant and beautiful minds in the history of science, a quiet Scottish mathematician and physicist named James Clerk Maxwell, living from 1831 to 1879. Maxwell's genius lay not in a single groundbreaking experiment, but in his ability to see connections where no one else had. In his time, the fields of electricity, magnetism, and light were largely considered separate and distinct branches of physics. Experiments had revealed various phenomena related to electric charges, magnetic forces, and the propagation of light, but no unifying framework existed. It was as if three different musicians were each playing a beautiful but separate melody. Maxwell was the genius who realized they were all part of the same grand symphony. Before Maxwell, several key discoveries had laid the groundwork. In the early 19th century, a Danish physicist named Hans Christian Ørsted discovered that electric currents produce magnetic fields. Shortly after, a French physicist, André-Marie Ampère, developed mathematical laws to describe the magnetic forces between these currents. Then came Michael Faraday, an English scientist of immense creative power who made seminal discoveries about electromagnetism. Faraday, who famously worked without the benefit of formal higher education, showed that a changing magnetic field could induce an electric current, a phenomenon known as electromagnetic induction. He also introduced the revolutionary concept of fields lines of force radiating through space, moving away from the older idea of forces acting instantly at a distance. These discoveries established a strong and undeniable link between electricity and magnetism, but a comprehensive, elegant theory that unified them was still lacking. Maxwell was the man who provided that theory. His genius lay in his ability to take these empirical laws, along with his own theoretical insights, and express them in a coherent and unified mathematical framework. Through a series of papers culminating in his monumental treatise, A Treatise on Electricity and Magnetism, published in 1873, Maxwell presented his four famous equations. These equations are not just a collection of formulas. They are a concise and beautiful summary of all classical electromagnetic phenomena. They are the language of light, the very grammar of the universe. Let's try to understand the essence of each of these four equations in a gentle, non-mathematical way. The first equation, often called Gauss's law for electricity, is about sources. It simply says that electric charges create electric fields. Electric field lines radiate outward from a positive charge and terminate on a negative charge. It's an elegant way of saying that electric charges are the sources of electric fields, much like a tiny spring is the source of its own tension. The total electric field passing through any closed surface is directly proportional to the total electric charge contained within that surface. This is a quiet, beautiful truth about the relationship between charge and field. The second equation, Gauss's law for magnetism, is a magnetic counterpart. It makes a profound statement: there are no magnetic monopoles. In simpler terms, magnetic field lines always form continuous loops. They never begin or end at a point. You can never find an isolated North Pole or an isolated South Pole of a magnet. If you were to cut a bar magnet in half, you would not get a North Pole and a South Pole. You would get two smaller magnets each with its own North and South Pole. This equation tells us that any magnetic field line that enters a closed surface must also exit it a beautiful symmetric law that has never been broken. The third equation, Faraday's law of induction, builds on Michael Faraday's experimental work. It describes how a changing magnetic field creates or induces an electric field. It is the very principle behind electric generators and transformers. Imagine a magnet moving near a coil of wire. The changing magnetic field from the moving magnet creates an electric field in the wire, which in turn causes the electrons to flow, creating a current. It is a quiet, beautiful connection, a profound link between magnetism and electricity. The fourth equation, Ampere's law with Maxwell's addition, often called the Ampere-Maxwell law, was the true stroke of genius. Ampere had previously shown that electric currents create magnetic fields that curl around the current. Maxwell's crucial insight here was to add a new term to this law. He proposed that a changing electric field also creates a magnetic field. This new idea, which he called displacement current, was purely theoretical at the time, a beautiful logical leap of faith. But it proved to be the missing piece of the puzzle. Without this term, Maxwell's theory would not have been complete, and it would not have been able to make its most profound prediction. A changing electric field, he reasoned, could create a changing magnetic field, which in turn could create a new changing electric field, and so on. It was a beautiful, self-sustaining cycle. The profound implication of Maxwell's four equations, particularly the last two, was that once an electromagnetic disturbance was created, it could propagate through the emptiness of space. The oscillating electric and magnetic fields would continuously regenerate each other like two dancers in a perpetual motion. This self-sustaining oscillation was in essence a wave. What was truly astonishing, however, was that when Maxwell looked at the mathematical form of his equations in a vacuum without any charges or currents present, he found that they naturally led to a wave equation, a mathematical description that dictated how this disturbance would propagate through space and time. And here came the moment of pure, breathtaking magic. When Maxwell calculated the speed at which these theoretical electromagnetic waves should travel, he found a remarkable result. The speed was determined by two fundamental constants derived from experiments related to electricity and magnetism, which had no direct connection to light at that point. These constants were the permittivity of free space, how an electric field passes through empty space, and the permeability of free space, how a magnetic field passes through empty space. These were measurable values from purely electrical and magnetic experiments, a quiet, almost unrelated part of physics. When Maxwell put the numerical values of these constants into his equations, the calculated speed for these theoretical electromagnetic waves turned out to be approximately 300,000 kilometers per second. This was an electrifying moment in the history of science because this calculated speed was almost exactly equal to the independently measured speed of light, a value that men like Roemer-Fizeau and Foucault had spent their lives trying to pin down. This stunning coincidence was no mere accident. It led Maxwell to a revolutionary and beautiful conclusion: light itself must be an electromagnetic wave. He wrote in 1865, "This velocity is so nearly that of light that it seems we have strong reason to conclude that light itself is an electromagnetic disturbance in the form of waves propagated through the electromagnetic field." Light was not just a ripple, but a specific kind of ripple, a beautiful rhythmic dance of electric and magnetic fields. Maxwell's theory provided a comprehensive and elegant explanation for light. It explained why light travels at such a specific and constant speed in a vacuum, a speed that is dictated not by a mysterious medium, but by the fundamental electrical and magnetic properties of empty space itself. It also explained the transverse nature of light waves, as the electric and magnetic fields oscillate perpendicular to each other and perpendicular to the direction of the wave's motion. Furthermore, and perhaps most astonishingly, it predicted the existence of an entire spectrum of electromagnetic waves extending far beyond the visible light we can see with our eyes. It predicted the existence of radio waves, microwaves, infrared, ultraviolet X-rays, and gamma rays, all of which were simply different frequencies of the same underlying electromagnetic phenomenon, all traveling at the same speed in a vacuum. Maxwell's work provided a theoretical basis for why the speed of light would be constant. The properties of empty space itself, the permittivity and permeability, were thought to be constant everywhere. This was a powerful idea, and for a time, it gave the ether theory a strong boost. The ether was now seen not just as a medium for light, but as the very physical manifestation of Maxwell's electromagnetic field. However, the profound theoretical tension remained if light speed was always c relative to the ether. Then an observer moving through that ether should measure a different speed. This was the very puzzle that the Michelson-Morley experiment had failed to solve, and it was a puzzle that would not be resolved by trying to find the ether, but by a young man who would dare to throw the idea of the ether away completely. The importance of Maxwell's equations cannot be overstated. They are considered one of the greatest achievements in physics, a beautiful act of synthesis that unified seemingly disparate phenomena into a single, elegant theory. They revealed the true nature of light and predicted the existence of a vast electromagnetic spectrum, an idea that led directly to the development of radio, television, radar, and all forms of wireless communication. But beyond their immense practical applications, Maxwell's equations set the stage for the next great revolution in physics. They gave us a constant, a fixed point in the universe, a speed that was derived from the fundamental properties of reality itself. And that constant, that number, that beautiful truth, would be the very cornerstone upon which Albert Einstein would build his revolutionary theory of relativity. The stage was now perfectly set for a revolution. We had arrived at a profound and beautiful paradox, a quiet war between two of the greatest intellectual achievements in human history. On one side stood the magnificent edifice of Newtonian physics, a framework that had successfully described the mechanics of the universe for over 2 centuries. In this world, velocities simply added or subtracted. If you were on a train moving at a certain speed and you threw a ball, the ball's speed relative to the ground was the sum of your motion and the ball's motion. This was a simple, intuitive truth that seemed to apply universally. On the other side was the breathtaking new theory of James Clerk Maxwell, which had triumphantly unified electricity, magnetism, and light into a single, elegant framework. A crucial, almost mystical implication of Maxwell's equations was that light is an electromagnetic wave, and its speed in a vacuum, a value we call c, is a fixed and unchanging constant. This speed was derived not from a measurement of motion, but from the fundamental electrical and magnetic properties of empty space itself. But what did this mean for observers moving at different speeds? According to Newton's classical mechanics, if a light source emitted light at speed c, and an observer was moving toward that source at a speed of v, then the observer should measure the light approaching them at a speed of c plus v. The two ideas simply could not coexist. They were like two perfect but contradictory melodies playing in the same orchestra. This conflict was further exacerbated by the strange and beautiful result of the Michelson-Morley experiment, which had been designed to detect the hypothetical luminiferous ether. The experiment had famously yielded a null result. No variation in the speed of light was detected, no matter how the apparatus was oriented or how fast the Earth was moving. The speed of light, it seemed, was the same for all observers, even those in different states of motion. It was a profound riddle, a cosmic puzzle with no obvious solution. Many physicists at the time tried to resolve this conflict by modifying the properties of the ether, or by proposing ad hoc explanations like objects physically contracting as they moved through this invisible medium. While these ideas could mathematically explain the experimental results, they lacked a deeper unifying principle and felt more like patches on a crumbling theory than a new elegant explanation. It was into this scientific climate of paradox and confusion that a young patent clerk in Bern, Switzerland stepped forward with his quiet genius. His name was Albert Einstein, and in 1905 he published his special theory of relativity. Einstein, a brilliant thinker who lived from 1879 to 1955, was deeply troubled by the inconsistency between Newton's laws and Maxwell's electromagnetism. Instead of trying to find a way to make the speed of light behave differently for moving observers or to invent new properties for the ether, he proposed a truly radical solution. He was willing to question the most deeply held assumptions about the nature of space and time themselves. What if both Newton's principle of relativity and Maxwell's constant speed of light were fundamentally true? And what if it was our everyday intuition about space and time that needed to be reevaluated? Einstein's approach was to elevate these two seemingly contradictory ideas into fundamental postulates, the bedrock assumptions of his new theory. These were not conclusions he had derived, but starting points he had assumed to be true based on the experimental evidence. The first postulate, known as the principle of relativity, stated that the laws of physics are the same for all observers in uniform motion, that is, moving at a constant velocity in a straight line. This was essentially a beautiful extension of Galileo's earlier principle of relativity to all the laws of physics, including those of electromagnetism. It meant that there is no preferred or absolute frame of reference in the universe. Imagine you are in a windowless spaceship, drifting through space at a constant speed. There is no experiment you can perform inside your spaceship, no juggling of balls, no throwing of objects, no bouncing of light that will tell you whether you are moving or standing still. All uniform motion is relative. This postulate elegantly discarded the need for an absolute stationary ether frame. The second postulate, known as the principle of the constancy of the speed of light, stated that the speed of light in a vacuum sea is the same for all inertial observers, regardless of the motion of the light source or the observer. This was the truly revolutionary idea, the key that unlocked a new way of seeing the cosmos. This postulate directly incorporated the observation from Maxwell's equations and the null result of the Michelson-Morley experiment into the very foundation of the theory. By accepting these two postulates as inviolable truths, Einstein immediately resolved the conflict. If the speed of light is indeed a constant c for everyone, no matter their relative motion, then the classical rules for adding velocities must be wrong when dealing with speeds approaching c. This seemingly simple step had profound and beautiful consequences for our understanding of space and time. To maintain the constancy of the speed of light for all observers, Einstein showed that space and time themselves could not be absolute, as Newton had believed. Instead, they had to be relative and interconnected, flexing and bending, to ensure that the speed of light always remained the same for everyone. This led to a series of beautiful and often counterintuitive consequences. One of the most striking was the relativity of simultaneity. In classical physics, if two events happened at the exact same moment for one observer, they happened at the exact same moment for all observers, regardless of their motion. Time was considered a universal, absolute rhythm. But in special relativity, this is no longer true. If two events are simultaneous for one observer, they may not be simultaneous for another observer who is moving relative to the first. Let's imagine a long train moving at very high speed. An observer on the train sees a flash of light occur exactly in the middle of the train car. For them, the light will reach the front and back of the train at the exact same moment the two events are simultaneous. But for an observer standing on the ground as the train passes by, the light traveling to the front of the moving train has to cover a greater distance, while the light traveling to the back has a shorter distance to cover. Since the speed of light is constant for the ground observer as well, the light will reach the back of the train before it reaches the front. Thus, for the ground observer, The two events are not simultaneous. This shows that now is not a universal truth, but depends on the observer's frame of reference. Another profound consequence is time dilation. This concept directly challenges the idea of absolute time. Special relativity predicts that time passes more slowly for an object that is moving very fast relative to an observer who is not moving with it. If you were able to travel in a spaceship at a speed very close to the speed of light and then return to Earth, you would find that less time had passed for you than for those who remained on Earth. Your clocks would have run slower and you would have aged less. To ensure that light always travels at c, for all observers, time itself must stretch or contract depending on relative motion. Similarly, length contraction is another consequence. Special relativity predicts that the length of an object when measured by an observer moving relative to it will appear to be shorter in the direction of its motion. If that same spaceship were flying past Earth at very high speed, observers on Earth would measure its length to be shorter than its length when it is at rest. The universe, in a sense, conspires to make the length shrink to ensure that the speed of light remains constant for all observers. Again, these effects are only noticeable at speeds very close to the speed of light, but they are a beautiful and real aspect of our universe. Perhaps the most famous outcome of special relativity is the mass-energy equivalence expressed by the iconic equation E = mc2. This beautiful, simple-looking equation states that energy E and mass m are interchangeable. They are two forms of the same thing. The C2 term, the speed of light squared, acts as a colossal conversion factor indicating that even a tiny amount of mass holds an enormous amount of intrinsic energy. This equation explained the immense energy released in nuclear reactions, like those that power the sun and stars, and it showed that as an object approaches the speed of light, its effective mass increases, requiring an infinite amount of energy to accelerate it further. This a beautiful logical reason why c is an ultimate speed limit for anything with mass. Einstein's special theory of relativity completely discarded the concept of the ether. If the speed of light is constant for all observers, there is no need for a special medium to carry light waves, nor is there a preferred frame of reference. Light is simply a disturbance in the electromagnetic field that propagates through the vacuum of space at a fixed speed, a speed that is an inherent property of the universe's fabric, rather than dependent on a medium. The solution to this great paradox was therefore not to modify light's behavior or invent new properties for the ether, but to fundamentally revise our understanding of space and time. Newton's laws were not wrong, but they were approximations that worked very well at everyday speeds. At speeds approaching the speed of light, Einstein's relativistic laws take over, revealing a universe where space and time are flexible and intertwined, all conspiring to ensure that the speed of light remains constant for all observers. This revolutionary theory laid the foundation for much of modern physics and reshaped humanity's understanding of the universe, demonstrating that the speed of light c was not just a curious measured value, but a defining characteristic of space-time itself. And so we arrive at the final, most profound piece of our journey. We have sailed on a sea of ancient philosophical debates, navigated the meticulous experiments of the Renaissance, and finally landed on the beautiful and bizarre shores of Einstein's special relativity. We have seen how light's speed, once a question of instantaneous presence, became a number to be measured, and finally a constant that defied the rules of our everyday world. But all of this leads us back to our first, most fundamental question, which now holds a deeper meaning. Why is the speed of light a cosmic speed limit? Why can nothing in the universe that possesses mass ever reach or exceed it? The answer, as we've gently explored, lies not in a single fact, but in the beautiful interconnected web of reality that Einstein's mind wove together. It is a story of mass energy and the very fabric of space-time. To understand this ultimate barrier, let's revisit the concept of relativistic mass increase, but with a new sense of wonder. In our everyday experience, mass is a fixed and intrinsic property of an object. A baseball's mass is the same whether it's at rest on a shelf or flying through the air. Newton's laws of motion, which work so perfectly on our human scale, assume this. They tell us that if we apply a continuous force to an object, it will accelerate indefinitely, its speed increasing without limit. But Einstein's theory whispers a different, more nuanced truth. It reveals that as an object accelerates and its speed approaches the speed of light, its mass as measured by an observer relative to whom the object is moving begins to increase. This is not an increase in the number of particles that make up the object, but an increase in its inertia, its resistance to further changes in motion. Imagine you are trying to push a heavy box across a floor. The faster you push it, the easier it gets, at least for a little while. But now, let's imagine a strange, magical floor. On this floor, the faster you push the box, the heavier the box gets. The more energy you put into it, the more resistant it becomes. To push it just a little bit faster, you have to push a little bit harder. But to push it just a tiny fraction of a moment faster, still you have to push much, much harder until the effort required becomes almost unimaginable. This is a beautiful metaphor for what happens to an object with mass as it approaches the speed of light. The closer it gets, the more resistant it becomes to further acceleration. The energy you are pouring into it, according to the beautiful simplicity of E, or mc2, is not just increasing its speed. It is literally being converted into its heaviness, its mass. The energy of motion itself becomes mass. This elegant and profound idea explains why the speed of light is so unyielding. Let's look at this with a simple yet powerful logical progression. As an object's speed, v, approaches the speed of light, c, its relativistic mass m, increases dramatically. According to the elegant mathematical formulas of special relativity, if an object with a non-zero rest mass, its mass when it is at rest, were to hypothetically reach the speed of light, its mass would become infinite. This idea of infinite mass has a profound and beautiful implication for acceleration. According to Newton's second law of motion, the force required to accelerate an object is proportional to its mass and its acceleration. If the mass of an object becomes infinite, then an infinite amount of force would be required to produce any further acceleration, no matter how tiny. And since it is physically impossible to generate an infinite force or provide an infinite amount of energy, it becomes an absolute barrier. No amount of sustained pushing or propulsion can ever accelerate an object with a non-zero rest mass to the speed of light. The closer an object gets to c, the more resistant it becomes, and the more energy is required to push it just a tiny bit further. It's like trying to climb a mountain that gets infinitely steeper. The closer you get to the top, you can get closer and closer forever, but you will never truly reach the summit. This effect is not just a theoretical speculation. It is a fundamental and rigorously confirmed reality, a gentle reminder that the universe operates on principles that defy our everyday intuition. We see it every day in the magnificent particle accelerators of the world, like the Large Hadron Collider. In these colossal machines, subatomic particles like electrons and protons are accelerated to speeds that are almost unfathomably close to the speed of light speeds, like 99.99999% of c. At such extreme velocities, their relativistic mass is thousands or even hundreds of thousands of times greater than their rest mass. An electron, for instance, which has a very tiny rest mass, can achieve an effective mass comparable to that of a small insect or a bacterium when accelerated to near light speed. The enormous amounts of energy pumped into these accelerators are not primarily increasing the particle speed, but rather dramatically increasing their relativistic mass. Despite the immense energy inputs, these particles consistently fail to actually reach c. They only ever get infinitesimally closer. This experimental observation serves as a direct and irrefutable proof of relativistic mass increase and the impossibility of reaching light speed for massive objects. The impossibility of faster than light travel for massive objects is also intrinsically linked to the concept of causality, the fundamental order of cause and effect. This is a crucial and deeply beautiful aspect of the cosmic speed limit. If it were possible for something to travel faster than light, it would violate the principle of causality, meaning that an effect could potentially occur before its cause. Imagine a scenario where a signal is sent from point A to point B. If this signal traveled faster than light, it might arrive at point B before it was even sent from point A, when viewed from a different frame of reference. This would create logical paradoxes, potentially allowing for communication with the past, which is inconsistent with all observed laws of physics. The speed of light c acts as a cosmic traffic cop, a gentle but firm referee, ensuring that the fundamental logical order of the universe is preserved. It is a constant that holds reality together, preventing a universe of paradox and chaos. And what about light itself, the beautiful traveler that sets this cosmic limit? Why can it move at c? The answer lies in its fundamental nature. Light is not made of particles that possess rest mass. The particle of light, the photon, is fundamentally different from all the particles that make up matter. The photon has zero rest mass. This is not an approximation. It is a fundamental unchanging property of its being. Because a photon has zero rest mass, it is not subject to the rule of relativistic mass increase. It can travel at the speed of light without its mass increasing, without requiring an infinite amount of energy. In fact, for a photon, there is no other speed. A photon is born traveling at the speed of light, and it can only exist at that speed. It cannot be slowed down to less than c, nor can it be brought to rest. Its very existence is inextricably tied to moving at the speed of light. It is the limit itself, not something trying to reach it. The journey to the speed of light, therefore, is not a possible destination for a massive spaceship, but a profound intellectual tool. It helps us understand why c is not just a fast speed, but a boundary where the very fabric of reality behaves in extreme and counterintuitive ways. The speed of light is not just a limit for moving objects, but also a fundamental property that defines the nature of duration and extent themselves. For a hypothetical observer, traveling at the speed of light, time would completely stop, and all distances in the direction of travel would contract to zero. The entire universe would be flattened into an instantaneous two-dimensional plane. It is a mind-bending thought, a beautiful paradox that shows us that our intuitive understanding of time and space, of mass and energy, are not fixed truths, but flexible, interconnected aspects of a larger, more elegant reality. The constancy of c, which we have now traced from the ancient philosophers' quiet wonder to the meticulous measurements of modern science, is no longer just a curious number. It is a fundamental law that defines how we experience time, how we measure space, how we understand mass, and how we conceive of the universe's ultimate limits. It is a testament to the fact that the most profound truths about reality are often found not in the answers that are easy to see, but in the questions that are difficult to ask, and in the patient, beautiful work of those who dare to seek them. It is a story of humanity's long, slow journey toward a deeper understanding of the cosmos, a journey that began with a flickering candle and ended with a universal constant that illuminates the very fabric of our existence.